Imagine a global variable and a local one sharing the same name. If you trigger a deletion, which one actually disappears? The local instance or the one at the global level? Let's analyze what happens when we run this print statement. Don't be startled by this error, it's a vital clue. Cannot access local variable. Here's the reason why. Because we defined and deleted the variable locally, you are strictly removing the local version of that value. The global variable remains untouched and inaccessible here. Now, let's change the game using the global keyword. We are back in the same scenario, but with a powerful twist. This time we declare the variable as global first. Predict the outcome. What happens to our data now? Does the deletion still target the local scope? Or will the global variable itself vanish? Let's run the code and check the results. There it is, a name error has occurred. Variable not defined. Notice that the variable is now gone. The global keyword gives the function direct access to it. The delete keyword then wipes that global variable completely. Consequently, it is no longer available to the program. Trying to print it outside the function now causes a failure. The data was destroyed because the function had authority. Python knew exactly which variable you wanted to target. Without the global keyword, the behavior is totally different. Let's revert the code to see that safety in action. Watch closely as we remove the global declaration. Now, the variable is defined normally. At this point, the variable is strictly local. Deleting it only clears the local function scope. This is why the final print statement still functions. The global variable was shielded from the deletion command. Only the local instance was removed from memory. Let's see what happens when we try to delete a function parameter inside Python. We'll start with a simple function that accepts an argument called data. The only job of this function is to try and delete that data parameter. Now, imagine we have a list defined outside of this function. We'll pass that list into our processMyList function as the main argument. Remember, the function is programmed to immediately wipe the parameter we just passed. Think fast. What do you expect the print statement to show? We are printing the original list after the function has finished its work. Let's run the code. Look at that. The output still shows every single number. The list is completely intact, exactly as we first defined it. Despite our delete command, the original data remains totally untouched. So, what is the secret here? When you pass an argument, Python creates a local variable for that function. When you use the delete keyword, you aren't actually destroying the data. All you are doing is removing the local reference to that object. The original list still exists safely in your computer's memory. When we called the function and passed MyList into the argument, the local data variable essentially became a temporary pointer to that list. The delete keyword simply cut the connection for that specific local name. It never reached out to modify the actual list living outside the function, and that is why your data is safe and sound. What do you think happens when we run these lines of code? Notice this variable in the global scope. It is considered global because it's defined outside the function. The function is right here, but the variable lives above it rather than inside it. By using the global keyword, you are granting this function direct access to the original variable. This makes the external variable available for the function to manipulate. Now, the global value is fully accessible. Without that global keyword, Python would simply create a new local variable instead. If we remove this line, the variable would remain strictly local to this function. And we can prove it. Running the code now triggers an error confirming it is treated as a local variable. Now, let's remove that delete keyword. Observe how I changed the value to online here, even though the original global value was set to offline. You'll see the original output remains offline when we print it from outside the function. Here's the crucial behavior. We reference the app status globally. We delete it, and then we assign a new value to it. What do you think the result will be? That deletion command is going to wipe out the global variable. What happens next? Running the code shows that while it was empty before, it now holds the value online. This happens because this specific line of code actually recreates the variable. Python does this because you explicitly flagged app status as a global variable at the start of the process. So every time you reassign it, Python creates a global version rather than a local one. This is a vital detail to keep an eye on. Whenever you use global before a variable name, it will always persist as global anytime you recreate it, even if you just deleted it. Mastering list loops is a total game changer. Today we unlock two essential methods. First, the classic for loop for clean iteration. Then the high control indexing approach. Both have unique benefits depending on your goal. Let's start with the basic for loop. It's elegant and incredibly simple. Just use the for keyword, followed by a temporary variable name. Then point it toward your original list. We have user IDs here, and we reference them in this line. For every user in that list, we trigger a print. Pay close attention to the indentation. In Python, logic must be properly indented to function. This indentation tells Python that the print line belongs to the loop. It creates a clear hierarchy. All we are doing here is displaying each user. Notice how the comma automatically adds a space. It cleans up the text after our processing statement. Even without a space after the colon, the output is perfect. See that? A clean, readable space is created for you. The loop cycles through every entry you have. It prints each ID using that temporary variable. Now, let's look at our next powerful example. What if you need to know the specific position of an item? The basic loop won't track the index for you. To track that, we use a slightly different syntax. We still use a for loop and a temporary name. But this time, we use the keyword paired with the range function. Range is a specialized tool within Python. Give it a number, and it builds a sequence to loop through. Let's look at a fundamental range example. Running this code gives us a very specific result. Entering the number 5 yields 5 elements. But remember, it stops just before that number. If you need to calculate values from 1 to 5, you would add 1 to your range limit. Remember, Python counting starts at 0. Now, let's try index-based looping. By using I, we always begin at position 0. This code lets us capture the exact index. We know precisely where each value lives. We can then take that position and multiply it by 1.1. Once executed, the original list is completely transformed. New, calculated values are ready for use. So use this index approach whenever you need to manipulate specific positions. Stick to the basic loop when position doesn't matter. 2 vital tools to add to your coding arsenal. Mastering the while loop for list iteration is a game changer. You might be asking, why choose a while loop over a standard for loop? Let's break down the key differences between these two powerful tools. I've covered this in depth before, but here's a high-speed refresher. Use a for loop when the specific index doesn't matter to your logic. We're printing users where the position isn't important. We're just focused on the data, not the order of the user IDs. Now, look at this list of prices. Here, the position is critical. We need to update the original list items. By targeting the index, we can change the original item instantly. Watch, we are increasing each value by 10%. We're multiplying every single price by 1.1. Notice how we've successfully transformed our entire data set. Now, let's dive into the star of the show, the while loop. It gives you total control over where your loop begins. While we usually start at index 0, we aren't stuck there. Check out the input and the resulting output on your screen. We iterate while I is less than the total length of the list. This allows us to trigger the loop from any index we choose. Run the code, and you'll see our custom starting point in action. We've jumped straight into position 2. Python uses zero-based indexing, so we go 0, 1, then 2, all the way to the list's end. Guided by the length of the list. You can even inject custom logic like skipping specific items. By incrementing by 2, we skip every other entry effortlessly. Just one small tweak changes everything. While loops unlock custom start points and dynamic behavior, they allow you to reshape how your code processes data. Want to skip entries? With a while loop, it's easy. Let's get started. Let's explore the index-based loop. This approach is called index-based because we are targeting the specific position of every item. We iterate through the entire list by first calculating its total length. This gives us the exact count of our items. Using that length, we step through the list one index at a time. That is exactly what the I variable represents. It's our index tracker. Now, here is a powerful alternative, the enumerate function. What enumerate does is transform how we handle the list. It takes our prices list and processes it automatically, moving through one item at a time. The major advantage? You can extract both the index and the actual value simultaneously. You get the direct data held within the variable. Those individual values are right there. For the first item, it retrieves index 0 along with the value of 10. Then it moves to index 1 and the value of 20. That's why we define two variables here. The index variable and the price variable. The first tracks the position, while the second holds the actual data. This allows you to easily modify the price within your original prices list. For example, we can multiply the price by 1.1. Notice the boost in clarity. With Enumerate, you have a clean variable name. In the first version, you are stuck using complex indexing to find your elements. With this method, you have a dedicated variable called price that was pulled directly into this line. Enumerate offers a massive advantage in code readability. The other way requires much more mental effort to track logic. Sure, storing the price in memory uses a tiny bit of resources, but it's a very small trade-off. Since we're already calculating values, the efficiency is nearly identical. Now you've seen both the modern enumerate syntax and the classic indexing approach most developers know. Unlock the power of the zip function to loop through multiple lists simultaneously. We have a names variable for our students and a scores list for their corresponding results. Our goal is to iterate through both, printing each student's name alongside their score. The zip function pairs these lists together, assigning the data to temporary variables, processing them one at a time. It starts by extracting the very first entry from our names list. When John is selected, the function automatically grabs his score from the exact same position. Run the code, and you will see the perfectly paired results right here in the output. John scored 85. Bob scored 90. James scored 78. This single line prints the scores in matching names dynamically pulled from our variables. Here's the key. The zip function combines the data and outputs one pair at a time into these temporary name and score variables. Notice we use plurals for the original list, but singular for the item being processed. Now, let's start at an individual score. To modify a value, we use the zip function as before, but we also add enumerate. This allows us to track the exact index of each item. Now we are receiving the name and the score, but the enumerate function also provides the index. That index gives us total control. We can now update the original scores variable directly by targeting the precise position using that index. Ever wanted to master reverse loops in Python? Check out this list of standard operations: initialization, process, and commit. These are our 3 steps. When you loop through them, they run in that order. For every step in steps, we execute that action. The output appears exactly as you'd expect. But what if you need to undo them? You would need to undo the commit first, then the process, then the initialization. To do this, we use the same list with a twist. Notice this line, for each step in reverse steps. This is the key. The reversed class returns a specialized iterator for any given sequence. Since a list is a sequence, you can easily flip it. Now, we change the print statement to undoing this step. Running the code now triggers undo commit first. The last item is now at the front. Next, we undo the process, and finally, undo the initialization. Remember, you can reverse almost any sequence just by using the reversed function. Want to filter out everything but the even numbers? You don't need bulky, complex code to get this done. Let's keep it sleek. We're using a power feature called list comprehension. Don't let the name intimidate you. It's simply a faster way to build a new list. See these square brackets? We start with a standard loop for n in numbers. Simple and clean. Now, we add an if condition to handle the logic. We check if the number has a 0 remainder when divided by 2. If it's even, it makes the cut. That value is then stored in our variable n. The code cycles through every item, testing the condition and saving the hits. Those outer brackets are the magic ingredient. They pack everything into one final list. Hit run, and there it is, a perfect list of evens. Efficient, readable, and pure Python.